Hello, everyone. In this video, we're going to be going over problem 17 in chapter 6 of the Fundamentals of Mass and Heat Transfer textbook. So this problem says to consider the conditions of example 6.4 in chapter 6. A laminar boundary layer can be tripped to a turbulent condition at x equals xr by roughening the surface of the plate at xr. Calculate the minimum and maximum possible average convection coefficients for the plate, at which temperature T equals 300 Kelvin or T equals 350 Kelvin do the extreme values of H occur. What are the corresponding values of XR? So to start with, just by going to uh, table A4, you can get most of these values for the states of 300 and 350. At 300 Kelvin, we're looking at a Prandtl number of 5.83. I said air before. I'm sorry, we're working with water. Density at 300 Kelvin is 997 kilograms per meter cubed. The dynamic viscosity is 885 times 10 to the negative 6 Newton seconds per meter squared. And the conduction coefficient is 0.613 watts per meter Kelvin. And at 350, once again, we're looking at a Prandtl number of 2.29, density of 974, mu of 365 times 10 to the negative 6, and a K of 0.668. So first thing for this problem, we want to determine what the critical transition locations are. So in order to do that, we just knowing that the critical Reynolds number is 5 times 10 to the 5, we can plug that into the normal Reynolds number equation, that being the Reynolds number is equal to rho, the density of the fluid, times the velocity of the fluid, times the distance of the fluid all over the dynamic viscosity. So plugging all that in will give us a distance of 0.44 meters at 300 Kelvin and 0.187 meters at 350 Kelvin. I forgot to write this down, but the length of the plate in example 6.4 is 0.6 meters. I can actually bring up example 6.4. The difference between what this is asking and what 6.4 is asking is that 6.4 is correlating the experimental data. This is looking at the model data or the mathematical ideal. So in order to determine what the convection coefficients are, we're going to need the Nusselt numbers. Now, in laminar flow, which is going to be up until the transition point, the Nusselt number correlation is 0.332 times the Reynolds number to the 1/2 power times the Prandtl number to the 1/3 power. And in the turbulent flow, the correlation is 0.0296 times the Reynolds number to the 4/5. I accidentally wrote 1/2 there, but it's to the 4/5 times the Prandtl number to the 1/3. Now, at first, I decided to find the max and min Prandtl number values, the max and min Nusselt number values, uh, for when we're looking at an x is equal to 0, that's the edge of the plate, versus x equals the critical number, which would give us the max and min of the term and of the laminar and the turbulent Nusselt values. However, instead, I decided to just do joint integrations as are seen in this problem, where h is equal to the Nusselt number times the conduction coefficient over the length. This can just become h is equal to the integral of the Nusselt number times k over L, to which can then be rewritten as h is equal to either the laminar or turbulent Nusselt number, which is in terms of a constant, the Reynolds number and the Prandtl number, which is a constant material property, and evaluate it using the laminar value from 0 to x, and 0 to xr, plus evaluating the integral from xr to 0.6. Now, at this point, I just plugged all that into my calculator, and I did not want to write it all down, but I got values of 490.772 watts per meter squared Kelvin for 300 Kelvin, and a convection coefficient at 1210.93 watts per meter Kelvin. So yeah. I would also like to quickly bring attention to something that I noticed while going through this problem. I'm going to go all the way down to table A6 for this, where unfortunately, you kind of have to double check any and all values that you're going to use if you get them from a table, not because the values of the table are wrong, but because this is supposed to be 10 to the negative 6, but there is no 6, meaning that unfortunately, if you don't know what the dynamic viscosity is going to be, you're going to be off by many magnitudes. It's the same with the thermal conductivity. Should say 10 to the negative 3, but unfortunately, as of this edition of the textbook, it's only saying 10 to the 3, which is incorrect. So that's something to keep in mind. I hope that this video was helpful in the approach that one should take to this type of problem. And I hope that this was helpful. Have a good day.